Good morning to everyone. Today I am going to discuss about group theory. This unit belongs to Physical Chemistry 1 for 3rd BSc Chemistry in Unit 1 for Module 3. In group theory, in this content we have going to discuss about what is meant by group theory, why we need for group theory, symmetry, symmetry elements, symmetry operations and groups, subgroups and also classes. Now let us see group theory. Group theory is one of the most powerful mathematical tools used in quantum chemistry and spectroscopy. Group theory is the mathematical method by which aspects of the molecule symmetry can be determined. A symmetry of a molecule reveals information about its property, that is structure, spectra, polarity, chirality, etc. Group theory can be considered the study of symmetry, that the collection of symmetries of some object preserving some of its structure forms a group. In some sense, all groups arise this way. It can be grouped into two categories. Getting to know groups, that means it helps to group theory and contain explicit definitions and examples of group. The next one is group application. It helps to understand the applications of group theory. The mathematical descriptions here are mostly inductive and so no previous knowledge is needed in the group theory. In the group theory, that is for an in spectroscopically, that electromagnetic radiations or the radiations having electric field as well as the magnetic field, both are perpendicular to each other or also perpendicular to the line of progression. These are the various electromagnetic radiations like radio waves, microwaves, X-rays, UV rays, cosmic rays, etc. These when interact with matter gives rise to various different phenomena like diffraction, interference, absorption, emission, depending on the type of electromagnetic radiation and matter. So why we need for the group theory? In this chapter, we come across many of the things which you are not aware of. The significance of group theory for chemistry is that molecule can be categorized on the basis of their symmetry properties. That means which allow the prediction of many molecular properties. The processing of placing a molecule into a symmetry category involves identifying all of the lines, points and the plane of symmetry. That it possesses the symmetry categories, the molecules may be assigned to no or as a point group. It allows you to determine that vibrational transitions are allowed or forbidden on the basis of symmetry. How electromagnetic radiation interact to show different phenomena like polarization, depressions and refraction, etc. And what is the transitions and transition probabilities? In group theory, the first phenomena is the symmetry elements. Symmetry is the common phenomena in the world around us. It is difficult to overestimate the importance of symmetry in many aspects of science, not only in chemistry. Symmetry is a very important aspect of chemistry and an understanding of it is important in spectroscopy, crystallography and molecular orbital calculations. If a molecule has two or more orientation in space or indistinguishable, that is symmetry. That means the rearrangement of a molecule after which it appear unchanged. That is the water molecule H2O. In the water molecule, there is the two orientations. It exists in the same type of the molecule. A symmetry operation moves molecule about an axis, a point or a plane to a position is indistinguishable. The symmetry elements is a main role in the group theory. These are geometrical elements with respect to one or more symmetric operations are carried out. That is symmetry elements. In the symmetry elements can be described in the 5 types. One is identity, n-fold rotation, reflection, inversion and improper n-fold rotation. First we see identity. Identity is abbreviated as E. This word is originated from the German Einheit, that is the first letter is E, that means unity. The identity is defined as the symmetry element simply consists of no change. Every molecule has this element. It is analogous to multiple by 1. That is, identity does nothing, has no effect. That is, operation brings back the molecule to the original orientation. All molecules or objects possess the identity operation. Identity operation has the same importance as the number unity, thus the multiplication. E is needed in order to define inverses. N-fold rotation, that is denoted as Cn. An axis around with the rotation by 360 degree by n results in a molecule indistinguishable from the original, that is known as n-fold rotation axis. In this, that a molecule can have more than one symmetry axis. The one is one in which the highest n is called the principal axis, and by convention is assigned by the z axis in the Cartesian coordinate system. Now let us see the example, the water molecule. Water molecule has the C2 rotation, that is 180 degree rotation. However, rotation of the water molecule about the axis by 180 degree gives the same molecule back. So that is the C2 symmetry element. Suppose if you rotate the 90 degree, that the position of the hydrogen atoms is replaced. So again in 180 degree rotation it comes back the same molecule. In the same type, the ammonia. In ammonia has the C3 rotation, that is 120 degree rotation. That is, in the 120 degree rotation, the ammonia molecule about the axis, it gives us the same molecule. In the xenon tetrafluoride, that is XeF4, that the 4 fluorine atoms after the rotation of 90 degree, that it gives us the same molecule, that is in the n-fold axis of rotation. The next one is the reflection. Reflection axis of symmetry, that is denoted as sigma. The plane of reflection through which the identical copy of the original molecule, that is the mirror plane or reflection, or otherwise known as plane of symmetry. If the plane contains the principal rotation axis, that is parallel, it is a vertical plane, it is denoted as sigma v. If plane is perpendicular to the principal rotation axis, it is horizontal plane, that is sigma h. If plane is parallel to the principal rotation axis but bisect the angle between C2 axis, it is a diagonal plane, that is sigma d. For example, water molecule H2O, in the H2O possess two sigma v mirror planes of symmetry because they are parallel to the principal rotation axis. And another one example for xenon tetrafluoride has two plane of symmetries to the principal rotation axis sigma v. In the xenon tetrafluoride, two planes of symmetry parallel to the principal rotation axis and bisecting the angle between two C2 axes. So, one is sigma d and another one is one plane of symmetry perpendicular to the principal rotation axis, that is sigma h. So, xenon tetrafluoride has the two sigma v, plane of symmetry has the two sigma v. And the next one is the inversion, that is denoted as I. The operation is to move every atom in the molecule in a straight line through the inversion center to the opposite side of the molecule. That is, the element that corresponds to the operation is the center of symmetry or inversion center. Therefore, xenon tetrafluoride possesses an inversion center at the xenon atom. In this xenon tetrafluoride, xenon F1, F2, F3, F4. F1 and F2 are in the opposite side. F3 and F4 are in the opposite side. In the inversion, that it can be geometry is changed. F1 and F2 are changed, position is changed. F3 and F4 are the changed in the position. The next one is the improper rotation, that is denoted as Sn. An axis around which a rotation by 360 degree by n followed by the reflection in a plane perpendicular to it leaves the molecule unchanged, that is improper rotation. There is one example, that is ethane. Ethane is in a staggered conformation and also in the eclipsed conformation. In the staggered conformation, one C6 axis is there. There are different. Therefore, this molecule does not possess a C3 symmetry axis. This molecule possesses the following symmetry elements, that is 3 sigma d, I, 3 perpendicular to C2 axis and S6. There is no C3 and sigma h. In eclipsed conformation, that is in the eclipse, ethane possesses the following geometries, that is C3, 3 sigma v, I, 3 perpendicular to C2, S3 and sigma h. Here there is no S6 and inversion configuration. So, compiling all the symmetry elements for the staggered ethane is the symmetry group called D3D. But in eclipsed conformation, that is in a D3H. So, what is the importance of symmetry? What do you learn about the symmetry? It is an important concept in crystal morphology, crystal structural analysis. It helps in classification of electronic state in a molecule. It is also useful in determining which atomic orbitals can combine to form molecules. It can be used in predicting the number of DD adsorption bands that are absorbed in coordination compounds. Ligand theory also depends on concept of symmetry. IR and Raman spectroscopy used for structural determination also depends on symmetry. Now, let us move groups and subgroups. What is meant by group? Group is denoted as G. Each molecule has a set of symmetry operation that describes the molecule overall symmetry, that is known as group. This set of operations define the group of the molecules. A group G is finite or infinite sets of elements together with a binary operation, that is known as group operation. In a group, there are 4 fundamental rules are there. One is closure rule, reciprocal rule, associative rule, identity rule. The operation with respect to which a group is defined is often called the group operation, and the set is said to be a group under this operation. First we see closure rule. In a closure rule, the product of any 2 elements and the square of each element must be an element in the group. That is, A and B are the group members. Then AB is equal to C, or A square is equal to D. So, C and D are also the group member. In a reciprocal rule, that is, every element must have a reciprocal, that is inverse, which one of the element of the group. If AB is equal to BA is equal to E, that is identity, then B is the inverse of A, that is reciprocal of A. Next one is the associative rule. Every element of the group obey the associative law of combination. In the associative rule, there are the 3 elements in the group, that is A, B and C. That is, AB and C is equal to A into BC. That is the associative rule. The last one is the identity rule. Every group consists of one element which commutes with all the elements and leaves them unchanged. That element is known as identity, such that EX is equal to XE is equal to X. Now, subgroups. Subgroup means any subset of a collection of elements which form a group is called a subgroup. The elements of subgroup should satisfy all the rules of the group. If here H is the order of the group, G is the order of the subgroup, then H and G are the natural groups. In a water molecule, as the symmetry elements are E, C2, sigma V and sigma V dash, that is identity, center of symmetry and the plane of symmetries are there. That is, group means E, C2, sigma V dash, and there are the 4 subgroups are there. One is E and E C2, second one, the third one is E sigma V, fourth one is the E sigma V dash. There are the 4 subgroups are there. The classification of the group. There are the groups are classified into 3 types. One is abelian group, non-abelian group and also cyclic group. First we see abelian group. Abelian group means a group in which all the elements commute with each other. Symmetry operations of water molecule form abelian group. In a water molecule symmetry elements, C2 sigma V is equal to sigma V C2 or E C2 is equal to C2 E. Sigma V dash is equal to sigma V dash sigma V, or C2 sigma V dash is equal to sigma V dash into C2. If the non-abelian group means, that is, do not commute, that is defined as a group is said to be non-abelian if all the elements do not commute with one another. For example, ammonia. In the ammonia, C3 sigma V dash not equal to sigma V dash into C3. So, the orientation of the hydrogen molecules is different. So, So it does not comes in a non-abelian group. So that is an example for non-abelian group. The next one is the cyclic group. A group is said to be cyclic if all the elements of a group can be generated from one element. That is where x square, x cube and so on xn. That is an identity. Here n is the order of the group. If the symmetry operations of the non-planar hydrogen peroxide, that is hydrogen peroxide means H2O2, that it forms as a non-planar hydrogen peroxide, it forms a cyclic group of order. In here the two symmetry operations, that is C21 and C22. So every cyclic group is abelian, but the converse is not true. The symmetry operation of trans 1,2-dichlorocyclopropane form an abelian cyclic group, whereas the symmetry operation of the molecule form the abelian group only. Next we see the classes. A complete set of elements which are conjugated to one another is called a class of a group. In a C2V point group, X inverse AX is equal to A, that is sigma XZ inverse C2 sigma XZ is equal to C2, or that is inverse under the naturals numbers, it can be removed and the sigma C2 is only there. And another one example, C2 inverse sigma XZ, C2 is equal to sigma XZ. Thus each element belongs to one class. The order of the group is 4. In the water molecule, order of the group is 4 and the classes of the operations are also 4. But in C3V, that is an example for ammonia, there are only 3 classes, but there are the order is 6 because there are the 3 hydrogen atoms are there, so that the orientations are different. So the classes are 3 but order is 6. So they are identity, 2 center of symmetry and 3 plane of symmetry. So the order is 6. The order of all the classes must be integral factors of the order of the group. So today we have to learn group theory and the importance of group theory and the classification of groups. In a next module, we have to discuss about point groups and also character table of multiple character table. Thank you.